Electro-optical MASINT is a subdiscipline of measurement and signature intelligence, and refers to intelligence-gathering activities which bring together disparate elements that do not fit within the definitions of signals, intelligence, imagery intelligence, or human intelligence. Electro-optical MASINT has similarities to IMINT, but is distinct from it. IMINT's primary goal is to create a picture, composed of visual elements understandable to a trained user. Electro-optical MASINT also generates information on phenomena that emit, absorb, or reflect electromagnetic energy in the infrared, visible light, or ultraviolet spectra, phenomena where a picture is less important than the amount or type of energy reported. For example, a class of satellites, originally intended to give early warning of rocket launches based on the heat of their exhaust, reports energy wavelengths and strength as a function of location. There would be no value, in this specific context, to seeing a photograph of the flames coming out of the rocket. Subsequently, when the geometry between the rocket exhaust and the sensor permits a clear view of the exhaust, IMINT would give a visual or infrared picture of its shape, while electro-optical MASINT would give, either as a list of coordinates with characteristics, or a false color image, the temperature distribution, and spectroscopic information on its composition. In other words, MASINT may give warning before characteristics visible to IMINT are clear, or it may help validate or understand the pictures taken by IMINT. MASINT techniques are not limited to the United States, but the U.S. distinguishes MASINT senses from others more than do other nations. According to the United States Department of Defense, MASINT is technically derived intelligence that, when collected, processed, and analyzed by dedicated MASINT systems, results in intelligence that detects, tracks, identifies, or describes the signatures of fixed or dynamic target sources. MASINT was recognized as a formal intelligence discipline in 1986. Another way to describe MASINT is a non-literal discipline. It feeds on a target's unintended emissive byproducts. The trails a thermal energy, chemical or radio frequency emission that an object leaves in its wake. As with many branches of MASINT, specific techniques may overlap with the 6 major conceptual disciplines of MASINT defined by the Center for MASINT Studies and Research, which divides MASINT into electro-optical, nuclear, geophysical, radar, materials, and radio frequency disciplines. MASINT collection technologies in this area use radar, lasers, staring arrays in the infrared and visual, to point sensors at the information of interest. As opposed to IMINT, MASINT electro-optical senses do not create pictures. Instead, they would indicate the coordinates, intensity, and spectral characteristics of a light source, such as a rocket engine, or a missile re-entry vehicle. Electro-optical MASINT involves obtaining information from emitted or reflected energy, across the wavelengths of infrared, visible, and ultraviolet light. Electro-optical techniques include measurement of the radiant intensities, dynamic motion, and the material's composition of a target. These measurements put the target in spectral and spatial contexts. Sensors used in electro-optical MASINT include radiometers, spectrometers, non-literal imaging systems, lasers, or laser radar. Observation of foreign missile tests, for example, make extensive use of MASINT along with other disciplines. For example, electro-optical and radar tracking establish trajectory, speed, and other flight characteristics that can be used to validate the TELINT telemetry intelligence being received by SIGINT sensors. Electro-optical sensors, which guide radars, operate on aircraft, ground stations, and ships. Airborne Electro-optical Missile Tracking MASINT, U.S. RCE-135's Cobra Ball aircraft have MASINT sensors that are docked to linked electro-optical sensors, the real-time optics system, and the large aperture tracker system. RTOS consists of an array of staring sensors encompassing a wide field of regard for target acquisition. LAT serves as an adjunct tracker. Due to its large aperture, it has significantly greater sensitivity and resolving power than the RTOS, but is otherwise similar. There is a broader program to standardize the architecture of the various RC-135 aircraft so that there will be greater commonality of parts, and some ability to switch missions. A Cobra Ball will be able to carry out some SIGINT missions of the Rivet Joint RC-135. Cobra Ball cues the Cobra Dane ground radar and the Cobra Judy ship-based radar. Sea radar MASINT tactical counter-artillery sensors. Both electro-optical and radar sensors have been coupled with acoustic sensors in modern counter-artillery systems. Electro-optical sensors are directional and precise, so need to be cued by acoustic or other omnidirectional sensors. The original Canadian sensors, in the First World War, used electro-optical flash as well as geophysical sound sensors. Purple Hawk complementing counter-mortar radar is the Israeli Purple Hawk mast-mounted electro-optical sensor, which detects mortars and provides perimeter security. The device, remotely operated via fiber optics or microwave, is intended to have a laser designator. Rocket Launch Spotter. A newer U.S. system couples an electro-optical and an acoustic system to produce the Rocket Artillery Launch Spotter. RLS combines components from two existing systems, the Tactical Aircraft Directed Infrared Countermeasures and the UTAMS. The two-color infrared sensors were originally designed to detect surface-to-air missiles for TADIRCM. Other TADIRCM components also have been adapted to RLS, including the computer processors, inertial navigation units, in detection and tracking algorithms. It is an excellent example of automatic cueing of one sensor by another. Depending on the application, the sensitive but less selective sensor is either acoustic or non-imaging electro-optical. The selective sensor is forward-looking infrared. RLS uses two TADIRCM sensors, an INU, and a smaller field of view single-color camera on each tower. The INU, which contains a GPS receiver, allows the electro-optical sensors to align to the azimuth and elevation of any detected threat signature. The basic system mode is for rocket detection, since a rocket launch gives a bright flare. In basic operation, RLS has electro-optical systems on 3 towers, separated by 2 to 3 kilometers, to give omnidirectional coverage. The tower equipment connects to the control stations using a wireless network. When a sensor measures a potential threat, the control station determines if it correlates with another measurement to give a threat signature. When a threat is recognized, RLS triangulates the optical signal and presents the point of origin on a map display. The nearest tower FLIR camera then is cued to the threat signature, giving the operator real-time video within 2 seconds of detection. When not in RLS mode, the FLIR cameras are available to the operator as surveillance cameras. Mortar launchers do not produce as strong an electro-optical signature as does a rocket, so RLS relies on acoustic signature cueing from an unattended transient acoustic measurement and signal intelligence system. There is an UTAMS array at the top of each of the 3 RLS towers. The tower heads can be rotated remotely. Each array consists of 4 microphones and processing equipment. Analyzing the time delays between an acoustic wavefront's interaction with each microphone in the array, UTAMS provides an azimuth of origin. The azimuth from each tower is reported to the UTAMS processor at the control station, and a PU is triangulated and displayed. The UTAMS subsystem can also detect and locate the point of impact, but, due to the difference between the speeds of sound and light, it may take UTAMS as long as 30 seconds to determine the POO for a rocket launch 13 kilometers away. This means UTAMS may detect a rocket POO prior to the POO, providing very little if any warning time. But the electro-optical component of RLS will detect the rocket POO earlier. Infrared MASINT. While infrared IMINT and MASINT operate in the same wavelengths, MASINT does not take pictures in the conventional sense, but it can validate IMINT pictures. Where an IR-IMINT sensor would take a picture that fills a frame, the IR-MASINT sensor gives a list, by coordinate, of IR wavelengths and energy. A classic example of validation would be analyzing the detailed optical spectrum of a green area in a photograph. Is the green from natural plant life, or is it camouflage paint? The Army's IMINT GSQ-187 improved remote battlefield sensor system contains a passive infrared sensor, DT-565 GSQ, which detects tracked or wheeled vehicles and personnel. It also provides information on which to base a count of objects passing through its detection zone and reports their direction of travel relative to its location. The monitor uses two different magnetic and passive infrared sensors and their identification codes to determine direction of travel. Shallow water operations require generalizing IR imaging to include a non-developmental thermal imaging sensor system to surface ships with a day-night, high-resolution, infrared and visual imaging, and laser rangefinder capability to augment existing optical and radar sensors, especially against small boats and floating mines. Similar systems are now available in Army helicopters and armored fighting vehicles. Optical measurement of nuclear explosions. There are several distinctive characteristics in the range of visible light from nuclear explosions. One of these is a characteristic dual flash measured by a bang meter. This went into routine use on the advanced Vela nuclear detection satellites, first launched in 1967. The earlier Velas only detected X-rays, gamma rays, and neutrons. The bang meter technique was used earlier, in 1961, aboard a modified US KC-135B aircraft monitoring the pre-announced Soviet test of Tsar bomber, the largest nuclear explosion ever detonated. The U.S. test monitoring, which carried both broadband electromagnetic and optical sensors including a bang meter, was named Speedlight, as part of Operation Burning Light. One MASINT system photographed the nuclear clouds of French atmospheric nuclear tests to measure their density and opacity. This operation is borderline with nuclear MASINT. Bang meters on advanced Vela satellites detected the what is variously called the Vela incident or South Atlantic incident on the 22nd of September 1979. Different reports have claimed that it was or was not a nuclear test, and, if it was, probably involved South Africa and possibly Israel. France and Taiwan have also been suggested. Only one bang meter detected the characteristic double flash, although U.S. Navy hydrophones suggest a low-yield blast. Other sensors were negative or equivocal, and no definitive explanation has yet been made public. Schlieren photography. Schlieren photography can be used to detect stealth aircraft, UAV, and missile flights even after engine cut off. Schlieren analysis is based on the principle that any disturbances to the surrounding air may be detected, like the shadow cast by the sun through the steam and hot air from a hot coffee, or even the mirage wave effect caused by the hot air on pavement on a summer day. It is essentially the reverse of adaptive optics, rather than minimizing the effect of atmospheric disturbance. Schlieren detection capitalizes on that effect. This form of MASINT is both optical and geophysical because of the optical detection of a geophysical effect. Schlieren photography may be used to provide an early warning of an imminent threat or impending attack, and if sufficiently advanced, may be used in the elimination of stealth targets. Laser MASINT. This discipline includes both measuring the performance of lasers of interest, and using lasers as part of MASINT senses. With respect to foreign lasers, focus of the collection is on laser detection, laser threat warning, and precise measurement of the frequencies, power levels, wave propagation, determination of power source, and other technical and operating characteristics associated with laser systems, strategic and tactical weapons, rangefinders, and illuminators. In addition to passive measurements of other lasers, the MASINT system can use active lasers for distance measurements, but also for destructive remote sensing that provides energized material for spectroscopy. Close-in lasers could do chemical analysis of samples vaporized by lasers. Laser systems are largely at a proof-of-concept level. One promising area is a synthetic imaging system that would be able to create images through forest canopy, but the current capability is much less than existing SAR or EO systems. A more promising approach would image through obscurations such as dust, cloud, and haze, particularly in urban environments. The laser illuminator would send a pulse, and the receiver would capture only the first photons to return, minimizing scattering and blooming. Use of LiDAR for precision elevation and mapping is much closer, and again chiefly in urban situations.